Friends, I am coming close to the end of this chapter. Work, energy and power. And we'll see today that there are many forms of energy besides the mechanical energy, which has got two forms. By virtue of its position or configuration, it is the potential energy, which is can be equal to mgh, can be equal to half k x square, as you have seen in the last two lectures. And then we come across, and we have known it from time immemorial, that there are many other forms of energy, and one form of energy transforms into another form of energy. It is said that energy is a romantic concept which can go from one set of defined energies to another set of defined energies, and the to and fro motion is there. Motion by motion I mean that the transformation of energy from one set of defined values to another set of defined values. For example, I will not go into the details, but I must mention to you to please look into your books and look for what is heat energy in calories, etc. There is, in the process of heat, there is a certain infrared radiation which is associated with heat. There is heat transfer, and heat in itself is a vast subject, as vast that it not only encompasses physics but chemistry also. The second form of energy which I have written over here is chemical energy. For the combination of two or more materials in the form that I have written over here, that A plus B is equal to C plus D. Some kind of a chemical relation exists, plus in the bracket I say that there is an energy which is released in every chemical reaction, including the burning of wood and many other things, where the chemicals in ionization, deionization, this, that, this, endothermic, exothermic, all these details are there. You can look into the things. Then we have electrical energy. For example, in class 9th and 10th, or even in class 8, you were introduced to the concept of resistance. That if a current flows through a resistor, there is a potential difference V which develops across that. So we have these relations. We remember that. Some people call it I square R, I call it Ri square, V square upon R, Vi, etc., etc. They are associated with the electrical appliance which is called resistor, and this gives us the joule heat. Two more equations over here I have written: half CV square and half Li square. C is for a capacitor, L is for an inductor, V is for the potential difference, I is for the current which is passing through this device, and these two devices, the capacitor and the inductor, they are storage devices. So you can store energy and use energy, etc., etc. Okay, there are many things, there are many details. Please look into the book. I am not going to waste your time on that. And then I come to a very beautiful relationship. And the beauty is that of energy mass equivalence. This is the velocity of light. 3 into 10 to the power of 8 meters per second, etc., etc. So it was found that energy and mass can be converted into energy, and energy can be converted into mass. Of course, optical energy kind of a thing associated with photons, which I say that E is equal to h nu, where h is the Planck's constant, etc., etc. Now comes a very interesting topic, and that is nuclear energy. In most of the chemistry, nuclear chemistry got to be different from normal chemistry. In the normal chemistry, the interaction is with outer orbit electrons of one material with another material. But nuclear energy is obtained out of the processes which may take place, where there is one process which is called fission and the other is called fusion. In the fission, a heavy nucleus, it's not radioactivity we are going to talk about. In the fission, when there is an interaction of a uranium, a very heavy nucleus with a neutron, then it splits into two parts, and a lot of energy is released. This is the kind of energy that was first used in the massacre of more than 200,000, some more people who died in the two beautiful cities of Japan in the Fat Boy experiment of the United States of America, where an atom bomb, two atom bombs were released in the two cities, and the two cities were razed to ground. Fission. This phenomenon of fission was a fashion at that time to be discussed. So much so that, if you remember, who wrote सारे जहां से अच्छा हिंदुस्तान हमारा, हम बुलबुले हैं इसकी ये गुलसिता हमारा, और जुगनू की रोशनी है काशाने चमन में, या शम्मा जल रही है फूलों की अंजुमन में. That was a poet laureate who was called the poet of the East, a philosopher, a thinker, a poet, not only in the Urdu language, but also a poet of Persian language, who could write fluently in English, also in German, who had his PhD from Germany. He was he had his family roots in Kashmir. He was a Kashmiri Brahmin, converted to Muslims, to Islamic faith. Now this man, Allama Iqbal, he describes fission, and I will describe fusion, because before fusion came into existence, Allama Iqbal was no more. So how does Allama Iqbal say about the fission? Now, I will just tell you that lahu means blood, and blood signifies or indicates the existence of energy. Now you know that fast developments were taking place in the knowledge at that time, and Allama Iqbal says, हकीकत एक है हर शय की, खाकी हो कि नूरी हो. Hakikat means the reality of everything is one. Whether that thing belongs to the earth, is earth, khak, or it is noor, that is what is there in the sun, the energy is pouring out of the sun. So haqiqat ek hai. That also signifies that the whole universe is built up of atoms of the same kind, same variety. But he says, haqiqat ek hai, har shay ki, khaki ho कि नूरी हो, लहू खुर्शीद का टपके, खुर्शीद means sun, लहू खुर्शीद का टपके, which means that the energy is radiated out of the sun. Why? How it is created? लहू खुर्शीद का टपके, अगर जर्रे का दिल चीरें, zarra means atom, zarra means that nucleus inside the atom. It's also a zarra, a particle. If we fission the heart, lahu khurshid ka tapke, agar zarre ka dil, dil means nucleus, the center part. Lahu khurshid ka tapke, agar zarre ka dil cheerein. So upon that fission which happens, where a zarra, a particle, is divided in two parts by some process, then a lot of energy is released. Allama Iqbal died before fusion could be understood. But today I can say, with a lot of respect to Allama Iqbal, that I can, because today we know that the energy in the sun and its stars is not because of the fission, but it is rather because of fusion of hydrogen nuclei into a helium nucleus. And in the process, a lot of mass deficit occurs, which when converted by E is equal to mc square, gives a tremendous amount of energy per reaction. So I will say, taking the lead from Allama Iqbal, I will say, haqiqat ek hai. The first line as such, haqiqat ek hai, har shay ki, everything. Khaki ho ke noori ho. Lahu khurshid ka tapke, that of the stars and the suns, the energy that we are getting from the stars and suns. Lahu khurshid ka tapke, agar zarron ka dil jodein, not split, but instead fuse two zarras and then get a higher atomic number, zarra, etc., etc. So friends, after this brief discussion for you, where there are umpteen forms of energy, and because energy has got umpteen forms, in the 18th century, energy was said to be, by the poets and others, to be a romantic concept in physics. So anyway, I'm not going to that. You can look for that yourself. Now, one of the things in the forms of energy, and I'm going to discuss the conservation of energy, so I'll have to say only one thing, that there is a transformation from one form of energy to another form of energy, to another form of energy to another form of energy. So this is there. Now, we say that in a system, if we look at the system as a whole, if the whole universe, okay, is taken as a system, then whatever loss is taking place at any instant of time, the same amount of gain will also taking place at the same amount of time. Okay, so that is why we say God Almighty as Rabbul Alameen, who provides for everyone. Out of what? What is that? What is provided to the God is energy, and that's why it is called a romantic concept in the literature at that time. So I can say I can sum up again and introduce to you that the energy as it is in any form can neither be created nor destroyed. Only the energy can transform from one form to another form. Okay, so with that much for the energy, after the work done, now I am going to talk to you about what is called power and define an average power if the work done W is there and that has taken place in a time interval of T, then the total work done divided by the total time is the average power and is defined as an instantaneous power for a very small interval of time dt in the form which we call the differential calculus form. So P is equal to dW upon dt. Also I can write dW is equal to vector F dot vector dr. Well, this is the displacement and this is the force under consideration, and therefore I can write that the power here I define as ddt, rate of change, time rate of change of F dot dr, and then I can include this F I can take out, and this I can write as the format being the same, the sequence being the same, F dot dr dt. What is this? F dot v, because dr dt is nothing but the associated velocity. Okay, so look here, the power is a scalar W, work done, divided by a scalar T. So if I take the analysis, then the work done is mLT minus 2 divided by T becomes mL square T minus 3, which is watts in the MK system or the SI system of units, and therefore this is defined as joules per second. Okay, there is another thing associated with it, which is horsepower is equal to 746 watts. Now I leave it for you to decide whether kilowatt hour is a unit of power or energy, and give you the simple answer that this is energy and this energy is the unit for which we pay the electricity, etc. Now I am almost through with the work, energy and power, etc. And in the meantime we have come across, and before that, certain conservation laws, certain conservation principles. Conservation of linear momentum we have already discussed, and conservation of mechanical energy we have already discussed. Then what I am going to talk next about is collision. Collision. And it's a very beautiful physics associated with collisions, which can be linear, slanting in 1D, in 2D, in this D and that D, in this environment and that environment. So now we come to the beautiful phenomenon which is called collision. And when we deal in collisions, the same kind of mathematics which we develop in collisions, the same kind of a thing is also developed in the case of scattering. So what is the difference between the two? In the case of collisions, if we have two particles, like I have tried to show you here, that this is a white ball and this is a green ball, and I have taken the size of the two balls to be same. Okay, why? Because their center of mass is at the center. The two balls, they really collide. Okay, there is a bodily collision between these two balls. In the case of several other phenomena, for example, in the famous Rutherford experiment of striking a nucleus, with an alpha particle initially in the beginning of the 20th century. That beautiful experiment was conducted in Manchester, okay, and there actually what happens is that a positive charge approaches another positive charge, and really the two of them cannot collide, because the field of one charge will repel the field of the other charge, and then that is another set of phenomena which we'll talk about. But in chemistry you must have seen that experiment conducted by Rutherford, and alpha particle experiment that is called. But right now what I am going to take up, because collision is a very complex process. In collision many things happen, and we have to thrash out all those things. So for example, in all collisions, the law of conservation of momentum, which means that the total, for the total system of particles which are there for all the bodies, and here in an idealized form I have taken the collision of two masses in an idealized form. When I say idealized form, then I take the size of the two particles which are colliding, or at least when the collision takes place, then it can be a head-on collision, it can be a slanting collision. And here what I have just shown, that before the collision the two particles, the two bodies, the two masses are in the same line, and the body M2 is at rest in the frame of reference that we are going to discuss it out. And this approaches this body, and thereafter in a generalized case, that will not happen in the case of a head-on collision, which we will discuss shortly, we solve the equations, etc. Then what happens, that the collision takes place. Collision does not take place for a zero instant of time, but rather there is an interaction time, say delta t, maybe small, of course, infinitesimally small, but it doesn't matter. There will be some kind of a deformation that will take place in this collision, and that will ignore. And in this system we will say that there is no air, this, that, and there is this surface on which the collision takes place is a smooth surface, etc., etc., so that no frictional values, etc., will be taken. This is our way of doing physics. In physics we choose lies to obtain the truth, to study the truth. So my lie is that this is an idealized case, and you have to believe in that. You have to do that thought experiment. So the mass m1 comes with the velocity v1 initial and hits it here. Okay. At that time v2 initial, the velocity of the second mass is taken as equal to 0. Thereafter the masses, because when that impact takes place, when the force time, the impulsive forces, mutual impulsive forces, which means a pair of impulsive forces, and that occurs for time interval of delta t, interaction time which I am writing over here, and thereafter they proceed according to Newton's first law. A body continues in its state of rest or of uniform motion unless impressed by an external force, and there is no external force in this motion, there is no external force in this motion. Of course, if you consider the frictional forces, then of course these bodies may come to rest, otherwise they will proceed in the directions which have been shown here. For the first body, M1, which comes and collides with the second body M2, I've just shown that taking this direction as the reference direction, it makes an angle theta 1. I'm not choosing theta 1 to be positive and theta to be negative. I'm just writing that the angle that it makes with the original direction of motion of this ball is equal to theta 1, and that of the ball which has been hit, which is M2, this is theta 2. Okay. So you find that because of the mutual impulsive forces, of course, I am saying that the linear momentum conservation takes place. The conservation of the mechanical energy, which kind of mechanical energy is there? It's the kinetic energy, may take place. I will define that and define for you what is what we call the elastic collision, completely elastic collision, and inelastic collision. These are some of the varieties of the collisions that we'll discuss, find out. So the first thing is that the change in the potential, change in the momentum delta P1, this is equal to F12 into delta T, and delta P2 is equal to F21 delta T. What is 1-2? The force on body 1 due to body 2. What is 2-1? Is the force on body 2 due to body 1, in keeping with my connotation that we took, I took in the case of Newton's third law. Okay? Now, of course, we have from the Newton's third law, which always exists, a pair of forces are there, action and reaction, or interaction and interaction, as I told you. Okay, so if I write F12 is equal to minus F21, equal and opposite forces, that signifies over here, I can write this equation as delta P1 is equal to minus delta P2. And if I transfer it on this side, on the left hand side, I will have delta P1 plus delta P2 is equal to 0. Change in P1 plus change in P2 is still having that vector form of P1 and P2. So I can write that delta, the change in the value of, P1 plus P2 is equal to 0. What does that mean? It means that no change is taking place in the momenta of the two particles, momenta of the two bodies before or after collision that has taken place. And that means that there exists a conservation principle. So the conservation principle which I have shown here is obtained by this, the mutual impulse. Of course, during the time delta t, the things are complex. The things we don't know, and we don't know, and we don't care. So as long as we can obtain, we can show that the conservation principle of linear momentum exists, and we'll discuss from here the various cases, specialized cases. For example, first of all, we'll take the head-on collision, okay, and then we'll take perfectly inelastic collision, and elastic and inelastic collisions, etc., for which I propose that be with me in the next outing. And before that, you must try to learn the things all by yourself. So you may have confusions. I am here to remove your confusions, because if you are confused, you know something. One of my teachers used to say to me, whenever I used to say that, sir, I am confused, he will say, very good, very good. That means you know something. And please, I emphasize again that my theme in delivering these lectures is you question, we answer. I seek that you do ask questions in the comment section, and I'll try to reach out and try to solve your queries if they are weighty. They should not be, you should not make fun in the system and try to learn, because our ultimate aim is to enjoy doing physics. I want to make things easy for you. So long, so long, so long.